Okay, welcome back. This is our seventh installment of tutorial, but I know it's week 8 of the course, so I apologize for that confusion. Anyway, this won't be as long as some of the other ones because a lot of what you I'm going to show you is stuff you already did last week. I'm just going to show you um, kind of in the context of how you'll usually use mixed models in sort of health and social science data, which is that we often think of them as hierarchical linear models. It's just another word that's a specific kind of conceptual way to think about mixed models. And that's the title of a book that I really like, that you have some PDF copies of a couple of critical chapters. The book's very expensive and it goes well beyond, what probably could be even taught in a single course. But it is a good purchase. It's getting older now, but only in the sense of it doesn't go through software and everything, but it provides some really concrete examples of how to interpret parameters. And so, as you saw last week, there is a data set that's used throughout some of those introductory chapters called the high school and beyond data set. And like I said, it is distributed with the NLME package in R. And last week you saw some code where I made it into how we need to analyze it with LME4. But we don't have to do that each week. So instead, I saved everything that I did as what's called an RDS file, which is just a way to save a data frame from R so that you don't have to remake it with the code. So sometimes, it's nice to be able to do that. With small data sets, you can easily just construct them from the original pieces that you have, but so as to not take up too much room. So just as a reminder, this week we're going to still use that school level variable mean SES, which is an aggregate variable, right? It's actually for each school, the mean SES is the average of each student's socioeconomic status number within the school. And remember, before we averaged those students' socioeconomic status, or right, so it turns out SES is already kind of on a zero-centered scale, zero meaning average. So the mean SES is using that, however they measured socioeconomic status. We're always also going to be interested in whether a school is public school or Catholic school. So these two variables vary at the school level. So everybody within a particular school is going to have the exact same mean SES, and depending upon how we code it, a binary variable indicating whether a school is a Catholic school. So, right, and so sector is actually an indicator for Catholic. Public is the comparison. Then we have this important student level variable, which is we took the original socioeconomic status variable that every student had, regardless of where they were, and we centered it, right? Meaning that the number that we're left over that we're going to use is the difference between the student's SES and the mean SES. So there's another example where we'll talk about that issue of if you have a quantitative variable at a cluster level and you're interested in the within cluster effect of that variable as well, you really need to center that variable relative to the mean of the cluster, because that allows you to properly disentangle the within cluster effect. So again, this week we're going to talk about math achievement and how it might be related to the student's socioeconomic status. So if you want to disentangle that effect of the student's socioeconomic status on math achievement from the at the school level, the average student's socioeconomic status and how that relates to the average math achievement for the school, Group mean centering is the way to do it, and there's a lot of things written about that. So first things first, we're going to read the data set in, so it's a new read RDS. Again, just reads a file that has been saved in that format, and it should pop right up. So if we go over here, and we'll see that, boom, reads it right from the internet, and it's exactly the same thing that we have been using before. So we're going to fit three models. First, the unconditional model again. So we did this last week. It's just want to change our notation a little bit. So last week we used the ANOVA symbols. This week and for the remainder of the course, we're going to use the hierarchical model symbols, because I think it creates less confusion with respect to what you're trying to answer and estimate from the model. So what we have in the unconditional model, right, is just that each person I in school J, their math achievement is a function of the overall level of math achievement in the population plus some increment up or down that relates to the school's overall position in terms of math achievement, and then plus another within school person level deviation. So a random effect is really just another type of error term. It's a random variable, just like the ordinary regression residual, but this time it applies to a different level. So it's nice to see it hierarchical, right? We actually have, this is the same model written in a different way, which is now what we do is we write down the cluster specific student equation, which is again, intercept plus student level residual error. Right? But then now we have an equation for the intercept itself. And so all this is we've taken the equation for beta 0j and substituted it in, and we get this guy. The reason we kind of do both is that this is what you're going to get from LME4, right? So as an example, right, when we fit the model, we're in when we just have a one-way random effects ANOVA, we don't have any fixed predictors, right? We don't have, aside from the intercept, we don't have any like student SES or, what school is the student in, or we have what school, that's the random effect, whether it's a Catholic or public school, right? So in the output, what we do is we get estimates of three things. So if you were to type summary, so again, it's the same model we fit last week. Math achievement simply regressed on a random intercept per school plus the regular residual error. So on the output, we get three things. We get the variance of the random effects, which in this case, is just a single number, which we denote with the small letter tau. 0, 0 meaning that that's a position in it. Later on, we're going to be seeing that the variance of the random effects could be a matrix, and so using the double index prepares us for later. We can talk about 0, 0, 1, 1, 2, 2. When anytime the two numbers are the same, that's the diagonal part of the matrix, and then if the two numbers are different, there's off diagonal. It just tells us variances and covariances amongst random effects. So that's the first thing we see here, is that across the schools, our estimate of tau is 8.614. And that's not really meaningful to us because it's not on the scale of math achievement, right? It's on the scale of squared math achievement. So we do get the standard deviation. So those are the first two things we get, variance and standard deviation. We also get the residual variance at the school level, within schools. And this is a pooled standard deviation essentially across the different schools. So pooled within, right? So students are going to be different with respect to math achievement within schools, and we pool that variation across the schools. This variance is a variation in the intercepts across the schools, right? That's essentially what the variance of the random effects is. And then the intercept is our estimate of uh, gamma 0, 0 up here, which last week was mu. So that's our estimate of the grand mean. That's our estimate with accounting for the fact that students are clustered in different schools. This is our overall estimate of the math achievement in this population of students. Okay. Now, again, I emphasized last week that in an unbalanced design or an observational study like this, where you usually don't have we haven't done an experiment, we don't have an exact same number of people per group. This number will be different from simply just taking all 7,185 students and averaging them, right? So we can do that mean HSB math hatch, and we get a different number, 12.75 versus 12.63. The reason that that is the case is because we're accounting for the fact that different schools have different levels of variability, and indeed then the estimates that come from each school of a school's math achievement, that is an estimate of the population math achievement. Basically, it varies with respect to how reliable that estimate is. And so the overall intercept from just a one-way random effects ANOVA, no predictors, gives us it's what's called a shrinkage estimator, but we can also call it a precision weighted average because it's a average it's a weighted average. We're basically doing a weighted type regression similar to what we do when we use weights in survey data. Is we give different schools that have more information, right, whose means are more reliable, we give them more weight in the overall estimate of the average level of achievement. So that's why it's different. Here, we weight everybody equally, so all schools are weighted equally. Here, we give more weight to the schools where our estimate is more precise. Our measurements in the school are more precise. Similarly, we can use these two numbers to compute the unconditional interclass correlation. That is actually related to the reliability of the means. We'll just leave it for now. It's also just an estimate of how much of the math achievement varies between schools. So there's quite a bit. So this kind of gives us an indication that there's a good bit that we can do to kind of predict or estimate or account for the school level variation. And if this number is pretty low, then we might not get a whole lot out of using any school level predictors at all. So if the number is really, really low, it might mean we may not even need some, depending upon who you ask, we may not even need a mixed effects model, but we'll put that aside. Okay. The second model we're going to fit is a little bit more fun, right? So we haven't done this one before. Now what we're going to do is, and again, you can, the chapter 4 from Raudenbush and Brick, as well as chapter 2, goes through all of these. All we're doing is just reproducing their results. So you have those as readings and to give you more background. But basically what we're doing is, if we think about the model hierarchically, we're still not using any student level information as predictors. So the student level equation within a school is the same, right? It's basically a student in school J, their math achievement can be broken down into the overall level of achievement for that school plus the little increment for being the random effect of being that student. Now, however, we're trying to, we now put in a predictor to try to account for some of that variation in the intercepts. And it's a simple binary predictor. Is the particular school, school J, is that a Catholic school or public school? So it gets its own regression coefficient. And if we plug this entire thing into the student level equation, substitute in for beta, we get this whole new equation, which is that a student's math achievement, student I in school J, is a function, once again, of that overall grand mean math achievement. But it's a conditional grand mean because it's conditional on what sector the school is from, an additional conditional random effect of being in that school, and then the additional person level random effect. So what's the difference between the fixed effect and the random effect for school? The fixed effect is just what it sounds like. We are assuming that schools are either Catholic or public, and we're trying to estimate essentially what the difference is on average between Catholic and public schools. A random effect is we take all of that information and then we allow for a school to be different, slightly from the average Catholic or public school. And again, that's a conditional random effect. So we are kind of acknowledging that there's still going to be variation across schools, even after accounting for the sector they're from. So we leave that in the equation. So from this model now, if we count up the betas, we're going to get the gammas, we get two fixed effect coefficients, the intercept again, and now a new one, which is the effect of being a Catholic school. And so since we've coded it as a binary variable, this is just a difference between Catholic and public schools in terms of the mean math achievement of that school. We still only have a single random, each school only has one random effect associated with it, the random intercept. And then each student that. So we still will only have the random part of the model will look the same. Now notice 6.677, right? That's a smaller number than in the unconditional model, which is what you should expect, especially if we look down here, we see, again, talk about in future weeks why there's no p-values here. But if you know anything about the t distribution, for a decent sample size, any t-value that's greater than like 2 or 2.5 in a normal situation would be significant, or you'd have a small p-value. So this is telling us that there seems to be, the null hypothesis that there's no difference on average between Catholic and public schools seems to not be consistent with our data. Indeed, if we were to say so, we would say that compared to public schools have on average 2.8 higher mean, or almost a mean of almost 3 points higher than public schools. Now you can see that the intercept has changed too, because if you set all these things equal to 0, right? All the predictors equal to 0, we get a public school. So this is giving us the average, the precision-weighted average estimate of public school means, and then this is the increment that we add to that to get the mean for a Catholic school, right? So we would estimate 11.39 plus 2 so that's like 14 or so. So it's almost a 3-point difference on average between Catholic and public schools. So because we have explained why some schools are different than other schools, the residual variance at the school level is smaller than when we didn't have any predictors. And in fact, we can use that as a type of effect size, right? What we can do is we can take the tau, right, the variance from the unconditional model, which will always be larger than any conditional model or constrained model. So we do the difference between those two with the larger number first, divided by the larger number. That gives us a proportion of the variance that has gone away, essentially, in this new explanatory model. So this model is basically like a reduction in variance, right? Basically, we said we've a reduction in the variance of the random effects by about 22%. So knowing about a school's whether a school is Catholic or public, tells us a fair amount about, at least gives us some predictive information about, on average, what that school's level of math achievement is. So we call that the means as outcomes model because there's no student level information there. So this model is really a model for the mean math achievement in school J. And what we're saying is that if school J is a Catholic school, on average, it should be about its mean level of math achievement for its students should be about, on average, almost 3 points higher than a similar public school. We contrast that with so let's keep it going. And so we can obviously, so this is an easy one with a binary variable. Let's keep it going. And what happens when we use a continuous variable? It's the same thing. So let's say instead we wanted to ask a question, and we could put both of these in the same model, or just sort of, kind of looking at it simply. If we put the mean level of math achievement for that school in the equation, like again, we do it the same, similar output, now we get a huge reduction in variance compared to the unconditional model. And that, is not surprising because we get an even larger t-value than we did before. Okay? And so let's talk about what this means, right? First of all, what does the intercept mean? The intercept is, right, gamma 0, 0, is the expected value when mean SES equals 0. Well, mean SES equals 0 when the school is about average on SES because of the way that scale is, right? So this is giving us an estimate of the math achievement for a school with average SES. This is telling us as average socioeconomic status of the school goes up or down, really up by 1 point, right? The average math achievement that we would predict for that school goes up by almost 6 points. So that's a big effect. Now, a lot of that has to do with the fact that if we look at the range, let's say, we can even, so let's just look at, or would describe, this isn't going to be a great example, but it's like describe HSB mean. Okay. Now we're ignoring the fact that it's duplicated, but its mean is 0, standard deviation is 4.1. The range, right, is 0.82 to 2.02. So it's never a situation in which mean SES goes up, by more than 1. But still, it's a good indication. If we were to extrapolate, we could also, divide that by, or so if we wanted to think about, well, what happens if SES goes up by 0.1 instead of 1? We would just, multiply this by 0.1, and so it would be about a half a unit, which is still a very big effect. Mm-hmm. So again, here's as we could see, right? Here's our range of SES. So kind of the biggest thing that we could do would be to jump from about negative 0.1 all the way up to 0.1. So that's 2 units. And that would be basically so the one end of the SES distribution to the other. It's about 11 points on average in terms of math achievement difference. So schools with very low socioeconomic status students are performing a lot worse. Or in the other way, a school with a very high socioeconomic status of its students on average is going to perform way better than a school down this end. Similarly, you can kind of get that from the same variance reduction. In this case, 8.614 minus 2.639. So that's unconditional model minus the second one, So we get a real big reduction of variance. So basically that if we know the mean SES of the school, we know quite a bit. At least it gives us cuts down on the unexplained variance across schools. Okay, finally, if we wanted to do multiple hierarchical linear regression, we can very easily accommodate other variables in that school level model. So again, we're ignoring anything about the students. We're simply, how is this different, for example, than just aggregating up everything? Well, it's different because we're still using information about the students individually. We're using information about them and how they vary around a central mean for the school, right? And that's informing our estimates down here. Right? So if we aggregated up, we would miss that. We wouldn't be able to disentangle these two things, and we might get different standard errors there. That's the aggregation issue that you saw as an exercise we did make a video about that, right? So here, we're just doing the same thing as we ordinarily would do. We have sector and mean SES. Now notice, right, that you might expect, well, is there going to be any variance left? Well, there's not much that's different here than just a mean SES model. So what's going on with that? Well, it's just like ordinary regression. Whether a school's Catholic or public is not independent from the school's mean SES, as we'll see at a later date. So when you have two predictors that are correlated, their effects are not independent. So the reduction in variance isn't additive, right? In fact, we might say that if we look at this number and we look at this number here, that once we know mean SES, the additional effective sector isn't huge. And you can see that here, right? That the t-value for mean SES is much larger than the t-value for Catholic versus public, right? And so again, we can't always say that in terms of t-values, but if you were to, again, look at the two differences, you can see that too, right? Looking at mean SES alone as a predictor, comparing that to no predictors, it's a 69% variance explained versus only 22% for Catholic. When we combine them in the same model, because they're correlated, we don't get that much more, but still important, right? So now we can see, now note, the intercept is still interpretable, right? It's the estimate for a school with sector equal to 0, which is that's the code for public. Catholic is 1 on this indicator variable, right? So public school with mean SES equal to 0, which is average. So the average public school in terms of SES would have a math achievement of about 12.13. If that's a Catholic school, we increment that up a little bit, and then as we go up or down on the mean SES scale, we go up and down proportional to this number. Remember, we can't go up and down really by 1 even, so it's more up by half a point would be half of this, so on and so forth. Okay. So the final thing I want to show you, and this is not, you don't have to do this. And indeed, there's some, kind of, we'll see some other ways to visualize mixed effects models. But because we only have predictors at the school level, this will work for us. So the effects package, which was also built by John Fox, who made the CAR package, which is a very nice package. What it does, there's other similar newer packages that compute these things called marginal means, or really, sorry, excuse me, they're not marginal means, least squares means. So what that means is this function in the background is simply just making some new data. making predictions based on the model for that new data and plotting it, right? And then there's ways to compute standard errors and stuff. So what we have here is we have the predictor effect for public versus Catholic. So again, if we looked at our estimates, we'd find that. So holding, this package takes into account the other predictors in the model. So this is just a visualization of this difference, 12 and 13 or so, for folks who, for schools that have a mean SES, usually it's held at the mean, so that mean there is 0, so it's sensible, right? So this is giving us basically for a fixed level of mean socioeconomic status, the difference between public and Catholic, right? The numbers here are relative. So this is specific to the instance where we hold mean SES at the number 0, its mean, right? If we wanted to change that, we can change the code and these numbers will change, but the relationship between public and Catholic remains the same. The Catholic schools are always going to have higher math achievement on average than, Catholic schools higher than public schools, no matter what value of mean SES we're at. The reason for that is because we don't have an interaction between those two variables. So we assume that it is just an additive model. Similarly, we can create a plot for the mean SES effect. And we see kind of what we said before, right? And it also gives us down at the bottom, what values of mean SES we have in the data set. Now, this is a little bit biased because the plotting doesn't understand that these values are duplicated, but we can still see the range, right, of mean SES. It's actually a little bit shifted here. There's only a couple of schools that are really low. Everybody else is there. So you can kind of, here is the best place where we could see effects. So again, like let's say I'm a school, and by the way, this would be most likely, since we're just under, or we're close to 12 here, we're plotting this holding school constant, school type, probably, I believe at public at the reference level at 0. And so, we can see these little increments. So if you're a public school person and you're interested in, well, if the student SES wasn't as much of a factor, or if it went up a little bit, here's how I could expect math achievement to go up or down. Obviously, we can't control SES, but that's just an example of like how you might do this. So you should be able to run all that code. Nothing should be really surprising. Again, the unconditional model, same thing as before. It should just come out with that. And so I do want to just show you, I think we can. So we'll fit this last model because we're going to need it. There we go. We got our effects there. So if we want to plot, let's see, predictor effect. Oh, it's not loaded. The package isn't loaded, so we'll probably get mad at me. Let's just go ahead and load it. There we go. Yeah, so you can change, different things about how many levels of variables, sort of where things are held. So it's a very, very cool package. There's actually a gallery if you want to see some more. John Fox unfortunately just passed away. He lived a very long, rich, full life, but kind of makes me a little sad every time I look at this stuff because he's the first R book I went through, yay, so many years ago. Huge impact. Wish I could have met him, but that's all right. So this is he's got still tons of stuff. This cool thing about R is there's Sanford Weisberg, I think, is still going, also getting up there. But I believe now someone will take over as the custodian of this package because it's so cool. So you can kind of try out with the models all these different ways um, to do stuff if you want to. So okay, so that's it. Again, not a whole lot that's new this week. Just kind of going through and showing you how we add predictors. It's just the same way as ordinary. We just have to make sure we have the random effect specified. Two things that we didn't do, which will happen in the next tutorial, which is that we didn't use any predictors at the student level. And we didn't change the random effects specialization. So those are two things we can do, which makes things really, really cool and fun. That's the topic of next week's tutorial. So I will see you then.